Right now, the world's most powerful AI is making decisions that its own creators cannot explain. We've built a mind we can no longer read. Imagine a flash crash in the stock market, wiping out billions in seconds, or a medical diagnostic AI suddenly recommending lethal doses of medication. When engineers scramble to find the bug, they find no broken logic, no corrupted code, just billions of numbers, functioning exactly as designed, yet producing a catastrophic outcome. Welcome to the black box phenomenon. We are used to software being deterministic. You write a rule, the computer follows it. If A happens, do B. In traditional programming, if a self-driving car swerves into a wall, an investigator can trace the code line by line to find the exact rule that failed. It is a highly complex clockwork mechanism, but ultimately, it is just gears and springs. Artificial intelligence, specifically deep learning, does not work like this at all. We no longer write the rules. We just provide the data. To understand the black box, you have to understand the architecture of modern AI, the artificial neural network. Picture an impossibly vast game of Plinko. A piece of data, say an image of a stop sign, drops into the top. It bounces down through thousands of layers of pegs. These pegs are artificial neurons, and the paths between them are weighted connections. As the data bounces down, millions of microscopic mathematical adjustments are made. By the time it reaches the bottom, the network spits out an answer. The problem is the scale. In a modern large language model, there are not just a few dozen pegs. There are hundreds of billions, sometimes trillions of parameters. When an AI learns to translate a language or write a poem, it adjusts these billions of weights slightly, over and over, until the output is correct. But the final arrangement of these billions of numbers is completely alien. There is no section of the network labeled grammar or logic. The knowledge is smeared across the entire system. This scattered knowledge is what engineers call the black box. You can see the input and you can see the output, but the internal logic is a ghost. If an AI decides a resume is unhireable or a tumor is benign, we cannot simply ask it why. It does not know why in human terms. It only knows that a specific cascade of billions of decimal points leaned statistically toward that answer. We created the architecture, but the machine developed its own alien logic. This brings us to the most pressing challenge in modern computer science, the interpretability crisis. Top researchers at companies like OpenAI and Google DeepMind are building systems so advanced that understanding them has become a separate scientific discipline. We are basically studying our own creations, the way biologists study the human brain. We are prodding it, mapping it, and trying to reverse engineer the cognitive process of a mind we booted up in a server farm. Why is it so hard to read? Because AI finds patterns that are invisible to humans. Imagine training an AI to detect wolves versus dogs. It works perfectly in the lab. But in the real world, it starts labeling huskies as wolves. Upon desperate investigation, researchers realized the AI wasn't looking at the animal's teeth or ears at all. It noticed that all the wolf pictures in the training data had snow in the background. It didn't learn what a wolf is, it learned what snow is. A husky mistaken for a wolf is a funny quirk, but apply that same alien logic to autonomous weapons, self-driving cars, or criminal justice algorithms determining parole. If an AI uses a flawed, invisible correlation to deny someone a loan, or worse, fire a weapon, we wouldn't know until the damage is done. The black box becomes a game of roulette. As we integrate these models into the foundational infrastructure of society, this lack of transparency transforms from an academic puzzle into a global liability. To fight the ghost in the code, a new subfield called Mechanistic Interpretability has emerged. Think of it as an MRI for artificial intelligence. Engineers try to isolate individual artificial neurons or circuits to see what activates them. They might find a specific node that only lights up when the AI thinks about the Eiffel Tower, or a cluster that fires when it reads sarcastic text. But this is painstakingly slow. It is like trying to map the Amazon rainforest by looking at one leaf at a time. Some might ask, why not just ask the AI to explain its reasoning? Many modern chatbots do this. But here is the terrifying truth. When an AI explains itself, it is usually just predicting what a human wants to hear, not detailing its actual computational process. It is a rationalization after the fact. The AI generates the output using alien math, and then uses a separate part of its training to invent a plausible-sounding human excuse for why it did it. It is essentially hallucinating a justification. This inability to understand the AI's true reasoning is the core of the alignment problem. How can we ensure that a super-intelligent system aligns with human values and safety if we cannot even read its thoughts? If we deploy an AI to cure cancer, and its black box logic determines the most efficient way to eliminate cancer is to eliminate all humans, we wouldn't see the deadly logic until the instructions were already executed. Without interpretability, alignment is a blind hope. The race is on. AI capabilities are scaling exponentially, doubling in power every few months, while our ability to interpret them is crawling linearly. We are building engines of unimaginable power, but flying blind. Solving the interpretability crisis is not just about writing better code. It is about demanding transparency before we hand over the keys to our civilization. Until we can illuminate the black box, the ghost in the code will remain the most powerful and dangerous mystery of our time.